The key to this problem is that both of these locations, Miami and Panama, the Panama Canal, are on the same line of longitude, 80 degrees west. So here's the North Pole and here's the South Pole. A line of longitude is something like this. It's from the north to the south. They're on the same arc, if you will. I'm going to erase that and pretend that the line of longitude on my picture is right out here, so that you can see that from the center of the circle, the line of latitude to Miami is 26 degrees. That means that Miami is from the center of the earth to this point is 26 degrees. And the line of latitude for the Panama Canal is 9 degrees above the equator. So I'm trying to show this above the equator, which would be about right here. So what we're going to work with is this piece of pie right here. Kind of wish they were straight lines. But one was at 26 degrees and one was at 9 degrees. And their difference between 26 and 9 degrees is 17 degrees, right? Hard to write. 17 degrees. So what's the distance between Miami and the Panama Canal? That's the, I'm going to go grab a red pen. That's this right here. Now, it's on the earth itself. If it was a plane, it would be 5 miles above the surface of the earth. But I want to find the distance from here to here in case I'm a pilot and I'm flying there. So I want to find S. So S is found by taking theta times the radius of the Earth, which is 3,960 miles. But before I go there, let's take the 17 degrees and multiply it by pi over 180 degrees, the conversion again, to convert that from degrees to radians. And I'll get 0.297. I'm going to actually use that whole number. I might even keep it in my calculator when I do the overall calculation. So I might not just use 0.297, I might use 0.2967059728 times the radius of 3,960 miles. And the distance then from Miami to the Panama Canal, I'm just checking is 1,100, pretty much 75 miles. 1,175 miles. Truly, that calculation has to be done as a pilot to determine their distance, and the control tower and whoever else has to do the calculations to make sure the plane has enough fuel, that they know the winds and how that's going to impact things. They've got to have that arc length. All right, let's do an unusual one. I had a Pontiac, and let's say the rear windshield wiper blade was 30 inches long, and the blade portion was 24 inches. So I'm going to try to draw a picture of this. So I've got this line right here, doesn't want to cooperate, and the blade portion is 24 inches. I'm trying to draw something of some thickness here. All right, it's not going to let me, so I'm going to go ahead and I've got at least a straight line. So the blade portion of this is out here, and it is 24 inches in length. And I'm going to extend this a little bit because the overall length of the windshield wiper blade is 30 inches. And what I want to calculate is the area of the windshield that blade will clear as a result of its rotating back and forth, back and forth, back and forth. I'm going to try to take this out here and show the blade about right there. So what you have to understand is it doesn't clear that area right there. The blade is only going to clear this area right here. That's all it's going to, so excuse my messy arc up there, but that's all the windshield wiper blade is going to clear. So how can I use the area of a sector to find the portion that it's going to clear when I know that this radius is 30 and this radius is 24? You have to be very careful on this one. A lot of people think they could just use a 24-inch radius maybe in the equation. A equals 1/2 theta times r squared. The one other thing I did not give you and I need to give you now is I'm just going to say that this is going to clear a 110-degree angle on the back of my windshield. Any chance you can see that what you've got to do is find the area of the large sector. I'm going to highlight that in blue. The area of the large sector. So let's find area of the large sector. And let's subtract the area of the small sector right here. Let's subtract the area of the small. Both of those going through a 110-degree angle. So let's go ahead and calculate that angle in radians. So let's multiply this by pi over 180 degrees. All right, so the angle theta in radians turns out to be 1.92 radians. And then I'm going to go ahead and do these calculations in color. So the area of the large sector would be 1/2 the 1.92 times the 30 inches squared. And I get a value for that one of 863.9 square inches. Let's now find the area of the small one. So the area of the small is 1/2 times the 1.92, the angle theta. But what's the radius for that one? Oh yeah, that's 6 inches, because it's the 30 minus the 24 would give you that 6 inches right there. And the area of that one turns out to be 34.6 square inches. When you subtract each of those, then what you get for the area of the pink, or the area of the windshield that's cleared, you get the 863.9 minus the 34.6, and you get a value of 829.3 square inches. That concludes the second objective of this section. Next, we're going to go into the topic of what is the angular velocity of an object, and we're going to look at an equation that's going to help us do some calculations. For example, if I want to find out how fast a point on the edge of my tire of my bicycle is traveling, I have to tell the computer on my bicycle the radius of the tire, and then it's got to measure the RPMs so it can do that speed calculation for me. So that's how the computer on my bicycle works, or the computer on my car works. That's where we're going to start up in our next segment.